Okay. Hello, everyone. So today we're happy to have Dr. Tomala to uh, tell us about his amazing work on the uh, sorry, let me give me a second. Yeah, tell us about like the AI-driven evaluation the impact of cyber attacks on AI-based machine vision system, a case study of stress the fast turners and please take it. Yeah.
Right. Oh, thank you, first of all, to Dr. Shao for the introduction and Sean Luddy and Mike Focusi for basically making this happen. In today's presentation, I'll be talking about the paper which we had submitted at IMechE 2025. This is basically evaluating the impact of cyber attacks on AI-based machine vision systems, which is basically a case study for threaded fasteners that we did. The paper ID that we have is 164156. It was basically published by all five of us as a co-author, and I was the lead author within it. This was published during my time at Ball State. All the faculties are from different universities. That is, Dr. Agarwal is from UNC Charlotte, Dr. Gill is from Centralia College, Dr. Lee is from University of Washington Tacoma, and Dr. Mayers is from Clemson. So it's an interdisciplinary team because AI is seeping into different domains. The four faculties, apart from myself, are from the mechanical engineering domain, while I am in the cybersecurity and AI space. So before we get into the actual paper-related information, some context associated with it is, like for example, assembly, the fasteners that we talked about are just considered as bolts, screws, nuts, and washers, which are basically components in the assembly process as a whole. And it's basically utilized in multiple industries, right? Automotives, aerospace, and so on. So any car that you have, for example, has those components within it. So improper selection of those components can lead to multiple problems. Some of them loose fitting, some excessive wear, some complete failure of the joint failure, or can also lead to some smaller failure within the automotive or aerospace domain, basically. So as a whole, problem is leads to costly repairs and safety hazards. So those are some of the challenges in general on how these systems, so assembly systems work, where you have different components being merged together to create a product. Obviously, like AI seeping into different domains, like for example, medical, same way it's seeping here. So for image-based classifications, convolutional neural nets are being utilized, CNN models. Some classic examples that are being utilized in this space is EfficientNet B0 and YOLO V5, for example. As we all know, AI systems have some issues along the lines that for example, it's explainability, right? We still don't know basically the AI models comes up with its decisions. So explainable AI techniques can be utilized to gain some level of transparency, interpretability, and eventually trust on these AI systems by continual usage and so on. So this was our paper that we had actually submitted in or published in IMechE 2024, where we implemented an AI-based system which would, classify fasteners, and then we would have explainable AI systems which would basically create heat maps and give us insights into basically the decision-making skill of those AI systems or AI models. So that's the paper that actually won us the award. One of the 10 papers won the award, and we were one of those 10, in 2024 in the AI category. So when we had created that paper, we already knew the next set of papers or research that we intended to do, which was trying to see if we can break the model. Once we have developed it, now let's try to break it. And then so that's what we did. So new type of attacks can focus on such AI systems, which are basically data poisoning and model evasion, right? So when we talk about data poisoning, at the source while data is being trained or the model is being trained, those images can be altered and which would lead to the reduction in model accuracy. A simple labeling change can also create a model which can completely misclassify. Similarly, model evasions can be done where you can create images which have perturbations within it and which would cause the models to misclassify on purpose. So in our paper, what we did is we actually utilized model evasions as a mode of attacks, basically. So in order to create such adversarial images that can be passed to a model which is already developed, there are different techniques that are available. Some of them are basically listed here, like deepfool, FGSM, that is fast gradient sign method, then PGD, that is projected gradient descent, and Carlini-Wagner. We actually utilize the FGSM method in our case. So the formula for that is basically being listed here. Adversarial images is basically x plus image plus epsilon value, which is anywhere from 0 to 1 that you add in, and then you have the loss function. So this would give us an adversarial image as a whole. Uh, Python, to be transparent, gives us this flexibility that the code is already developed. You can just import the right libraries and you can basically create an adversarial image as needed. The only drawback is if you increase the permutation value or magnitude, the images become more blurry. So you kind of have to select an appropriate value that works for your test case. That's basically the idea. The next thing is obviously everyone's been touting that explainable AI is, sorry, not explainable AI, human in the loop is basically a mode of that could help in aiding in Industry 5.0 for assisting with cyber attacks and AI-based models. Humans should be in the loop in every context. So we were thinking on how we could implement that. And then the other thing that we were thinking was how explainable AI can be utilized for identification of cyber attacks. Can they actually identify perturbations? So can the techniques that are some of them are listed here, that is GradCam, SHAP, and LIME, do they have the capability to identify perturbations basically? In our context, when we say perturbations, we mean cyber attacks as a whole. So if you look at the image here, the general notion of how a basically heat map looks in the context of an image is being shown here. So you have a screw here shown on the left side, and to the right is basically a heat map, which was created using the GradCam technique. The more when you have an object, the more red it is, it means that that part of the image was utilized in making the decision more. So the blue is used the less, the red is used more, and yellow and cyan and all those colors are going to be in the middle. So ideally, you would want the red part to be on the actual object of the image, because when we take an image in this context, you'll have background too, right? So we do not want this, for example, the red part to be somewhere on the extreme left side and so on. So explainable AI basically does that for us. So gives us an insight into the model's thought process, basically a little bit. So the research questions that we developed with all these concepts were, can basically the FGS generated images break or reduce the confidence score of the efficient net B0 based machine vision systems? That was one of the questions. To be transparent, when that question was created, I was like, yeah, sure, we'll be able to break that system, no doubt on that. Then the next one was, is or can the XAI system implemented as a part of machine vision system detect FGSN generated attacks? This was something we were unsure of. I was unsure of. So when we were implementing, I did not know if that would happen or not happen. So because there's little on that on the literature. There, in the literature, you can find details about how XAI is used to identify, make the decision explainable, but it's not being utilized much in the case of identification of cyber attacks or adversarial perturbations. So that was new, but luckily we were able to see that it was able to identify perturbations. Then the third thing is, can human in the loop be a solution to mitigate such attacks, or can humans be brought into the foray to in such systems which are used for classifying different fasteners? So the process we did was we created a data set which had 12 different categories. That is 5 screws, 5 nuts, and 2 washers. So as a whole, we had 12 categories. Simple data set, I would say. Then we had taken images of image using an iPhone 12 camera with the 1x magnification. The resolution was 3024 times 4032. Distance was 4.25, and the total image captures was 106. So small data set, but when we want to talk about creating a machine learning model or machine vision model, we needed more size. So we did some augmentation, which I'll talk about in next slide. But that's the original data set that we had. And then we also create an adversarial data set, that is adversarial images. We had basically 12 images for each one for each of the categories, that is 12 categories. So five screws, five nuts, and two washers. And this adversarial images was created using the FGSM technique. The perturbations that we used was 0.07, 0.08, 0.09, and 0.10. So we had 12 images, adversarial images with 0.07 perturbations, 12 adversarial images with 0.08, 12 images with 0.09, and 12 with 0.10. So as a whole, we had 48 images generated for us. Sample images are being shown here on how adversarial images looked. In most cases, they look very similar, apart from the fact that if you look closely, there's a little blurriness on those images as a whole. So the data set that I talked about, we had to augment it because the images that 106 that we created was very low. So we augmented the data. When I say augmented the data, we wrote a Python script that would basically, you know, create more images with 5% inclination. For example, if you have a screw, more images was created in which only the image of the screw was turned 5 degrees and so on. So that led to us creating like 2,400 images as a whole. And then that was the image that we actually trained or created a model on. And out of that, we basically had an 80% to 20% split for training and validation. So that's how when you create a model, that's how it works. You can set the percentage. So that's the percentage that we selected. So when we talk about training, 1920 images were involved in it for basically training purpose, and rest of the images were for validation and so on for the model. So kind of looked like this. We basically had these images, which was passed to the convolution. Feature extraction was basically done, convolution layer and pooling. And then probabilistic distribution was done on it. And then we had an output layer, which the model was generated for us as a whole. So when we thought the next thing was testing these things on, just for clarity, this model was created on MATLAB for us because that was efficient for us based on our workload. You can actually use Python. The language does not matter in this context because you could do the same thing with both the languages. So next thing is basically the adversarial images which we created for testing. This was, first of all, the model was created, adversarial images was created using Python by me in that context. So when we had the original image, we had 100% accuracy, which was achieved. Just for clarity, when we say 100% accuracy, so that there's no confusion, we mean that whenever we pass any of the images from the 12 categories, it was accurately classified. There was no inaccurate classification, and obviously they might have different probability score or confidence score, which out of one were 0.80, 0.99, and so on. But there was no misclassification, basically. Then the next thing was the adversarial images. When we passed that, what happened is, for example, when we passed adversarial image with 0.07 for all the 12 categories, its confidence rating went from zero misclassification, that is 100% accuracy, to 41%, that is five basically were correct and seven inaccurate. So perturbations caused the model to break in a way. Then we tried 0.08, which had literally no impact on the result. We literally had the same result, that is five correct and seven inaccurate. So the percentage remains same. When we tried creating the adversarial images with 0.09 perturbations, which lead to the correct value, that is only three of the 12 categories were identified accurately and nine inaccurately. So that was basically 25% accuracy at that point. And then 0.10, which led to two being correct and 10 inaccurate. So that was like 16.67. So we went from a model which always accurately classified objects with obviously different confidence score to a model which basically was misclassifying uh, or was just accurately classifying just 16.67% of time. So this is how the model was created. So we basically had the test data, which was passed to the convolutional neural nets, and we would get basically the heat maps for it. So if you look at the heat maps on the left, that is machine screw and lock washer, you can see that the heat map focused on the object or is close to the objects. And for example, lock washer, its basically accuracy score is 0.999, and for screw nut it's 0.9910. But when we actually passed adversarial images to it, the accuracy fell down 0.36 for screw, and which was actually machine screw, but it was identified as a lock nut. Basically, misclassification, and accuracy score was also low. In addition to that, if you look at the XAI component, XAI was able to identify that the heat maps are looking at are at a different location than it should. Ideally, it should just be on the screw here, but somewhere located different else, and it was actually looking at the perturbations. So the model actually made the decision based on all this scattered information that you see, and the red part especially here. So this gave us a little bit of insight on how the model came up with its decision at this point. So when we actually try to look at this, similar thing was done for all the 12 cases. So if you look at this, all the accuracy scores that we had for original images with his non-adversarial images, all of them had decently good score. The maximum being 1.0, which is 100%, and the lowest that a model classified was 0.842. In this case, if you look at the classification score went down, the heat maps were skewed all over the place. That's what the result was. For example, if you look at CapNut, that was one of the two images that was still classified as accurately, but look at its percentage. It went down from 0.99 to 0.64. So basically, even the images that were or the categories that were identified accurately had a reduction in their classification score, or basically confidence score. The other one, which was accurately identified, was Locknut nylon insert, which is 0.999, which, if we look at, basically gave us 0.543. So as a whole, we can say that the adversarial attacks impacted all 12 categories in a way. So the takeaway from this slide is that original images had high confidence scores and focused on GradCam feature maps were very focused on the objects itself. While when we talk about adversarial images, there's low confidence score that went out, and the images were very skewed, GradCam images. The next thing that we were looking at, can human in the loop concept be utilized to actually uh, basically can it be utilized to uh, identify cyber attacks? So in order to do that, we came up with a theoretical framework that is being shown here. So we had the test data, then we had the convolutional neural net, then we basically had the XAI systems or that was generating images. And then based on the threshold value, you can actually pass the image to a human operator who can then provide oversight as needed. So in this context, when I say oversight, the notion is different models will have different threshold value through which they actually work. For example, the model that we created, hypothetically, it might work anything below an 80 needs to have a human intervention and so on. That's doable. On the other hand, for some models, 70% might work. So there's no, at least for the moment, a standardized value that could be utilized for basically one value that fits all. Obviously, that's an area of research that could focus on try to find out or come up with a formula that might work decently for multiple or many of the models that are there. So that's one of the areas that we are currently kind of thinking on how to see or if we can make progress on as a whole. But the idea is that anytime an image falls below a certain level, it'll go to a human expert, and human will basically make the decision at that point. So in this case, it's 0.36, and the heat map is skewed. So human operator can make a decision based on those two things, whether it's a cyber attack or whether it's just a misclassification or and so on, or if it's just an issue with the camera. So that was the theoretical framework that we came up with. So in order to test this, of course, we needed some human participants who would be willing to participate and try to identify some cyber attacks for us. So what we did is we actually requested students from University of Tacoma, mechanical engineering, because that's what we are focusing on. These fasteners are more related to their field. So we selected junior and senior students because at that point they have decent understanding of their domain and which especially the fasteners and stuff. So that was basically the idea for selecting and a niche set of students who are to belonging to a particular major. The total participants in this thing was 37. So we asked them questions along these lines of do you see a cyber attack or not, or what are your opinion on it, and so on. So there were a couple of set of questions here. I just have a sample question set that's there. The two questions that were asked is, do you think these images have cyber attack embedded within them? And if yes, what is your confidence score? Even if it's no, what's your confidence score? That's what we asked. So we had a couple of questions. One, when we passed in without any explainable AI training. We just passed, give them knowledge about cybersecurity, how the attacks work, and so on. And then we asked the same question and passed these images to them as a whole. And then they came up with a decision, whatever they did. And the second set of the survey, we actually gave them heat maps. We just added an explanation on how heat map works in addition to the cybersecurity concept and AI security concepts. And then we tried to see what their decision would be at that point or what results they would give. And the questions remained the same at that, both the point. The only difference was that we actually added an explainable AI system here. Not explainable AI systems, explainable AI images as a whole here for people to review. So when we look at this 12 nuts and bolts that were added here, without explainable AI training, 70 for machine screw, 70% of the individuals were able to, classify accurately that it was adversarial image. But their confidence score was around 5.59, among 10 was the highest. Then for flange bolt, it was 64.86, which had around 5.92% average. And the highest confidence was basically at HexNut, which was at 6.41. So as a whole, we had decent results where students were able to identify um, different whether there were cyber attacks or not, but on those images. But obviously, their confidence score was low. And once you reach a point where you are near the 50s, it literally means students are guessing, right? Because it's a flip of a coin when you have two options, yes or no, at that particular situation. So we were looking at how explainable AI systems or explainable AI concepts can help in human decision making, right? So the second set of questions, we had the same thing, and the results went up. So for example, the machine screw had 70%. The results of people who identified the cyber attack, that is adversarial image, accurately was 89.19, and their confidence score went up to 8.49. Similarly, for flange port, it was 64. That was one of the images that actually went down, 54.05. And the reason for that was that the heat images that's there was basically showing very similar result. If you look at this, flange bolt 0.909 and nylon, this was same image when passed, gave us nylon lock nut basically for nylon insert with 0.554. The heat maps were very close. So in this case, heat maps were not able to detect a cyber attack properly. That was the reason students got confused in this context. And similarly, there was another such instance that happened. But apart from that, in most cases, that is, yeah, lock nut, nylon insert, that's where another confusion was done, where students had a reduction in the accuracy rate. And it was again due to the XAI not being able to properly identify those cyber attacks or perturbations. So in general, the overall confidence score in all the situations went up for the students. And the two scenarios in which the students were unable to identify a cyber attack or the reduction in the accuracy rate or percentages was because of those two situations were because of the XAI images not properly being able to detect those perturbations. So in general, when we talked about these results, some of the things or the major things to take away from this project that we had was model evasions attack could be performed on, on the AI model that we had created for fasteners using FGSM. Efficient net B0 model showed a significant drop, of course. It went from being, not at all misclassifying the categories to basically misclassifying it for most of the extent. Heat maps basically through GradCam can effectively expose anomalies in most cases. We are actually conducting a next phase of that research where we are trying to see how different background affects such model evasion attack. Can heat maps be utilized when we have a black background, which we are testing currently? It's not working as accurately as it should, but we're still in the testing phase for it. So we are trying to look at that aspect of research too. Then the next thing is how human in the loop framework can be utilized, to basically identify model evasion attack as a whole. In addition to this, we're also looking at how human in the loop concepts can be utilized for physical AI concept that is from a system design point. So those are some of the research that we're kind of focusing on in addition to this. And the last conclusion that we had as a whole was cybersecurity information without XAI were comparatively less effective in this context. Um, so that's what some of the results that we had from this paper that we had published a few months ago. Uh, Thank you. If you have any questions, please feel free to ask.
Yeah, thanks for the nice talk. Let me first start with a question here. So I noticed that for the adversarial perturbation, basically, okay, we try to find out, okay, what's the minimum perturbation to cause this certain, okay, or misguide the model, right, to do some wrong decision. So I also observed in your picture, right? So basically, I guess you basically, I guess the noisy part is basically the perturbation you add, right? So, but I'm just curious. So, is there any additional ways, so for example, make the attack less detectable in a sense? For example, okay, it's not just in absolute volume. For example, I guess you mentioned in certain A1 norm, A2 norm, certain metric to measure the perturbation. Is that possible? We can also build some invisible perturbation to the image, but meanwhile, you can also mislead the model to do the wrong prediction.
We can. PGD is known to do be a little better with that aspect. So PGD attacks are more spread out on the image. So we had used FGSM. If we had used PGD, it would be a little more invincible, like you're saying. But obviously, when you create perturbation attack, it's not going to be completely invisible. That's the
Hmm.
thing.
Hmm.
And we performed this in a white box settings because we had idea about the parameters.
Mm,
One of the next things to do is try to create basically images for in a black box settings where we do not have idea about anything about the model and still trying to break it. But
mm.
yeah, to answer your questions, yeah, obviously there's some blurriness. PGD might be useful for it, but obviously there will not be an image with completely no, completely invisible thing like you mentioned.
I see. Yeah, thanks.
Thank you for the question. Yeah.
Yeah, are there any questions?
I do see one question in the Q&A. VJ, do you want to read that or do you want me to read that?
I do not see any questions in the Q&A for some reason,
Okay,
but
I got it. I got it. Question from Nathan. Are there any papers in which you would suggest to read more about this topic?
to be transparent, our 2024 paper is a good paper to read. Uh, I've gotten so many requests on that. Like people have been asking, like, can you please share those papers and stuff? So I would definitely suggest my paper from 2024. I'd be happy to share the link later on with you, Mike, so you can share with the students. But
Yeah, that'd be great.
that would be a very good paper for students who are interested on, incorporating cybersecurity and AI security concepts in multiple domains. So that would be a very good start, in my opinion.
Great. Sure. Yeah. Yeah. Send that to me and I'll add it to our webpage.
Yeah, thanks so much.
Yeah, thanks, John.
Okay, I don't see any other questions here. Yeah, so thanks a lot. Thank you, VJ. Really appreciate you joining us here. Take care and hopefully you can get some sleep there now.
Yeah, thank you,
Oh,
Vijay.
yeah.
Yeah, I was just gonna say, go take a nap.
Yeah, that is the plan, 3:30 a.m. in the morning.
Yeah.
So
All right.
Great, stay in touch with
One
us, VJ.
more. Seems there one more question.
okay.
Yeah.
Oh,
Do you have a
there
question,
is.
Hanshin?
I think there's one more question in the.
Yep, it's in the chat.
Oh, I'm
Yeah,
sorry. I didn't see that in
yeah.
the chat. Okay. Okay, yeah, the question from Ved is how prevalent do you think these types of attacks will become in the future? Are there any specific areas that may be targeted?
To be transparent, the answer is yeah, attacks on AI system is just bound to increase. That's a great question. That's there. I see it increasing a lot because these model evasion attacks, for example, model poisoning attack, model inference attacks did not even exist before the AI came into play, right? And with how every organization is trying to implement AI within their organization, for example, we're going from software AI to physical AI, so which are all interconnected via networks, and all these attacks are just bound to increase. So obviously there are different aspects to it when we are talking about one technique is when we're trying to create a system where we are incorporating AI within an organization, we have to think about what are the weaknesses that these AI bring in addition to the strengths. So identifying those and addressing those at the beginning would be a good start. But obviously, as we all know, even though if everything is implemented, systems can break and so on. But long story short, I do personally think that these attacks are bound to increase in the future, and you'll hear a lot about them once all these organizations have full-fledged implemented AI within them for them, basically.
Well, thanks a lot. Really appreciate it. Thanks for joining us, and we'll see everybody next week. So take care.
Thanks
Yeah,
again.
thank you, guys.
Bye.
Bye.
Oh, bye, Sean. Thank you.